All right, welcome, welcome. My name is Anthony Bouchon, and thank you for joining us here today at the GCP Online Meetup, number 27. Today, we're going to be covering high-performance computing on Google Cloud Platform. I'm joined today by my co-host, Stephanie Wong. Steph, do you want to say hi to the group?
Sure. Hi, everyone. I'm Stephanie Wong. I'm a customer engineer based out of Sunnyvale, and this is my first time co-hosting with Anthony, so I'm excited to be here.
Woo! Yeah, and we are excited to have you here. And so today, Arend Dittmer, he is a customer engineer with an HPC background, and he will be kind of guiding us through what I think to be at least a very complex topic, but one that is very relevant to cloud computing. So Arend, thank you for joining us today.
Okay, Anthony, thanks so much for having me and giving me the opportunity to present here and talk a little bit about HPC. A little bit about my background. I joined Google Cloud as a customer engineer about five months ago. Before that, I worked for IBM, and I spent a lot of time in the high-performance computing space, specifically with schedulers, IBM Spectrum LSF, as well as high-performance parallel file systems, namely GPFS.
I love it. That's quite a background, and so you definitely bring a lot of experience to the table, not just specific to GCP, but just from the industry.
Yeah, thanks. So should we delve right into it?
Yeah, I think one thing I do want to remind people is that, this is, if you haven't seen a GCP online meetup before, these are typically casual. And, we like to have you interact with us. So we are on YouTube Live. And the beauty of that is that you can ask us questions in the chat. And Stephanie and I will kind of inject it in the conversation. So again, thanks for joining us today. And Arend, we'll let you take it away.
Okay, cool. So before we delve right into the subject, I would like to level set, because there's so many different definitions of high performance computing, and I was actually myself going back and forth as to what is actually the right one. The one that resonates the most with me is the notion of the use, or defining HPC as the use of distributed processing to solve complex computational problems. And if we look at the specific areas where you find HPC applied, there's first of all the financial services industry, a big consumer of high-performance computing resources. The typical use case in that industry is running a large number of Monte Carlo simulations to assess the impact of changing market conditions on a portfolio of investments. Things like, if the market moves right now like it did 2 years ago, what would that mean for your portfolio? Then another area heavily vested in HPC is manufacturing, computational fluid dynamics, things like airflow simulations around cars, airplanes, water flow simulations around boats, or even including airflow simulations within electronics like laptops or cell phones. Then there is, within manufacturing, the area of finite element analysis, where you try to simulate the impact of physical force on a product. An example of that would be a car crash simulation, for example, or a drop test of a cell phone. Then there's the area of electronic design automation within manufacturing, basically the design of chips of ASICs and their logical verification. That's a typical high-performance computing workload. In bioinformatics, there's genomics, genomic sequencing, identifying genomic reference sequences in a human genome, for example, for personalized cancer medicine. Computational chemistry tying into drug discovery in that space. Then in oil and gas, there's seismic imaging. You basically have a seismic impact through an explosion or a heavy metal plate being dropped on the ground that sends seismic waves subsurface, and then these reflections of these waves are detected by detectors. These signals are processed and then later visualized, and give geophysicists really an idea of what's going on under the surface of the Earth, of course, with the objective of identifying areas where you could find hydrocarbons, aka oil. Government education, probably the biggest consumer of HPC resources. Think Los Alamos National Labs, or Lawrence Berkeley or Lawrence Livermore National Labs. They run massive simulations across a wide variety of disciplines. And then lastly, media and entertainment, basically the rendering of animations. Just think like Cars or Shrek or movies like that. So this is at a high level. Yeah.
And one thing that I'm noticing here is that it's really kind of, it's present across several different types of industries, right? All with different types of use cases. And so kind of as far as what are the patterns that we're seeing? What is, when we say complex computational problems, like what are we talking about here that unites kind of all of these different industries and the types of data that they're working with or files that they're working with? Like what is HPC really kind of, where's the value add across all these different industries?
I think that the common denominator, and this is why the definition of the term itself is so high, so it can be so difficult, is really this aggregation of processing power to solve these problems, right? The notion of creating one compute cluster that's dedicating to solving this set of complex problems, right? That's
kind of like supercomputing.
Yeah, exactly. It's the same concept, right? I mean, the whole concept of distributed processing in HPC was introduced with, in the early 90s by Don Becker and Thomas Sterling, that had this idea of, hey, why don't we replace that supercomputer with a bunch of disparate compute resources that we, connect to a network and then make look like one unified resource through, for example, cluster management software. Right?
Yeah,
awesome.
And I think one thing I've noticed is that a lot of the data sources for these types of industries are going to be coming in from a variety of different locations and geolocations. So it's going to be a highly distributed data source portfolio as well. So I think that's one factor.
Yeah, absolutely. That's a good point. So next, I just want to quickly give you a lowdown of a typical high-performance computing stack, software and hardware. So at the top, you typically have you always have the applications that you run. So for crash simulation, something like LS-DYNA, STAR-CCM+ for fluid dynamics, BLAST for genomic alignment, or Madagascar for seismic processing. These applications, of course, are linked against their runtime libraries. If they are tightly coupled, meaning that an application runs distributed across multiple nodes with a lot of inter-process communication going on between the individual tasks that the application run comprises, then you would also use the paradigm called MPI, message passing interface, that facilitates that cross-node process communication, so to speak. So you would link with these libraries and use the MPI APIs for that. So that's very common, particularly when it comes to finite element analysis, where you're solving tightly coupled differential equations. It's kind of part of the underlying physics that if you distribute the workload, you automatically introduce this tightly coupling, and you would use MPI for that. Then underneath, you have the scheduler workload managers. Their job is basically to distribute the workload across the cluster. To put it in simple terms, you avoid a situation where you have 100 nodes in a cluster and you have 100 jobs running on one node and all the other nodes are being idle. So the schedulers serve the purpose of evenly distributing the workload across the cluster under consideration of the resource requirements for a specific application, of course. And resource requirement meaning like you could, one application might perform better on a large memory host, so you want to make sure that only your nodes with large memory are candidates for execution for this specific application. So the workload managers handle that. The workload managers also handle setting the allocating the resources under consideration of a priority that's specified, right? I mean, of course, like any business, some jobs are more urgent than others, and that could be reflected in a configuration at the scheduler level to give higher priority jobs, higher priority over lower priority jobs. So I think it's pretty straightforward. Cluster management provisioning is another layer. The issue here is how do you initially get an operating system on your nodes that are part of your cluster, and then how do you keep that configuration of the OS consistent? Underneath, typically have shared file systems. For shared file systems, things like NFS, cluster, Lustre, GPFS. And then underneath that, we have the physical layer. So we have the network fabric, 10 gigabit, 40 gigabit, or InfiniBand. InfiniBand typically being used for applications that require or whose performance is very dependent on low latency and high bandwidth. For example, car crash simulation, like I mentioned, when you're dealing with applications solving tightly coupled differential equations, there's a lot of traffic going on between the nodes that comprise an application run. Those benefit greatly from InfiniBand interconnects. Okay, and what are the the challenges with running a cluster on-premise? Well, the most obvious challenge is that operating HPC clusters is expensive. And in many cases, really, the performance of the HPC cluster has an impact on an organization's bottom line, right? Think about a company that's designing ASICs in a highly competitive environment, right? The more simulations they can run, the better their product is going to be, or the more features they can add, which directly impacts the organization's bottom line. So for that reason, it's important that they keep the hardware current at all times, which of course is very expensive. Following, the typical Intel cycles, for example, for CPUs of 18 months, gets pretty costly if you want to update your hardware, refresh your hardware every 18 months to keep your cluster performing at its best level. The other issue is in some organizations, GPUs may be beneficial, but they may only be used for very specialized workloads. If you have to buy them, it really gets very, very expensive very quickly, and you may not even have the need to keep these GPUs busy at all times, so they may be running idle a lot. The other thing is that workloads in general are very bursty, driven by project cycles, and it's hard, particularly in actually in any organization other than the really, really super big companies that have a very critical mass. It's hard to keep a cluster busy at all times, which results in wasted cycles and wasted expense. Another thing is
that, you know what?
Yeah, Anthony?
Just to jump in there with the kind of hard to keep a cluster busy at all times, it really goes back to that. And it looks like you're going to cover a little bit of CapEx, but I mean, when you own hardware, it's yours, right? And this is something that it's stateful computing. It's always available, and you're paying for it, right? You paid for that time that you have there. But I'm hoping, and I'm just venturing out a guess here, but within HPC, there's kind of the ability to deploy clusters that live to process a certain job, and then maybe they die, or you can deploy a different cluster that's sized properly for a different type of job. It becomes really complex when you're managing across your own data center, your own server farm, right?
Exactly. And also the provisioning cycles within an organization, just from an organizational perspective, can be pretty long, right? I mean, if you have a new working group that's working on something leading edge and needs hardware, it can take months before that goes through procurement and all of it, whereas the cloud gives instant elasticity, right? And instance availability.
I'm also thinking about storage costs just for your backup scheme and having to almost double your storage costs just to continue to maintain backups as well.
Yes, exactly. Exactly.
And paying for a failing disk. I used to be in IT department. That was a large cost, larger than I thought. So at any rate, let's take a look at what this looks like on Google Cloud Platform. I think.
Yeah, just one more note here. I think, and again, I'm not an accountant, but it is a big deal for a lot of organizations. If we contrast on-prem with cloud, is that cloud is OpEx. Right, and on-prem is CapEx, right? That's from an accounting perspective, often beneficial for organizations. So yeah, let's have a look at why you would want to run a high-performance computing workloads on GCP. So first of all, on GCP, again, it boils down to cost. You have the elasticity, but you also have the real on-demand pricing. You don't have to commit upfront to a certain usage. You can still get very good pricing without doing that, because we have something called sustained use discounts. So what that means is if a vCPU, for example, is used more than 25% of the duration of a month, more than 25% of a month, we automatically apply discounts on the hourly cost of that CPU. And you don't have to do anything. There's no commit involved. We just do that. The other thing is, that goes to the point of refresh. We frequently refresh our environments, so we right now have and always have the latest generation of processors and GPUs available on GCP. Right now, we're the only cloud provider running Intel Skylake. We have NVIDIA P100s available. So this alleviates or takes off the pressure if you move to GCP of refreshing on-prem all the time. Another big deal for high-performance computing specifically is the notion of preemptible instances. We offer preemptible instances, which means instances that are only available for a 24-hour time period. And can be preempted at any point in time. We offer those at an 80% discount. Question, of course, is how often do they get preempted? We don't have an SLA around that, but I've seen anecdotal evidence that the preemption rate is between 5 and 15% over the period of a week if you allocate a bunch of VMs there. So
and
this is
that's about in line with my experience too. So
okay, thanks for supporting that. So this is ideal for mission critical workloads. The other thing it allows you to do is you can really build a hybrid. You can build a cluster in the cloud that uses some standard instances, and then you can supplement that with additional preemptible instances to leverage the lower cost, and you can determine what the balance should be. And of course, in HPC environments, you typically have schedulers that are available to restart jobs that failed due to node failure. So they would take care of that. And it's even more beneficial if you run applications that support checkpoint restart, which means applications that periodically save their state. And then if there is a node failure and they are restarted on a different node, they can just resume reading in the state that was saved. And that limits the amount of work that is, the computational work that is lost due to the restart. Okay, we'll be talking later in the context of a demo about HT Condor, which is a scheduler that has also also comes with checkpointing libraries that you can link in. So that would be really a great target if you have a homegrown application that you can link against these libraries and then leverage that with preemptible instances. I think that would be a pretty cost-effective way of doing things. Then we offer high network bandwidth on GCP. So if you have at least 8 vCPUs, we offer a 16 gigabit per second network bandwidth. And we have the option to what we call a dedicated interconnect that allows you to build a hybrid cloud. It basically allows you to peer with us from networking perspective at one of our points of presence and extend your on-premise infrastructure seamlessly into the cloud using a private RFC 1918 address space. Okay, so quickly mapping the stack on Google Cloud. So of course, on the application side, nothing changes. One important thing is you also need to check the T's and C's with the application vendor to ensure that you can really actually move your application and run it in the cloud, that you don't violate any T's and C's there. Scheduler Workload Manager is basically, you can deploy any schedule you want, and it manages the resources in a VM cluster then. For cluster management and provisioning, as we'll see in the demo, you can use Google Cloud Deployment Manager to instantiate the cluster, which is very straightforward, and you can use Stack Driver for monitoring the resources in the cluster. And then underneath, you have a shared file system. So the shared file system is something that you would build on GCE instances, or you would use Google Cloud Storage. Right now, we don't have a managed shared file system offering, so you would, at this point, have to build your own using GCE instances with direct attached storage.
So,
yeah.
One question I think that was raised by Yuri in the chat, and I think it's a good topic just for the purpose of clarity, is when we throw around, distributed computing, oftentimes Hadoop is a framework that's brought up, right? We have a scheduler similar to what we have in this stack here. I think Yarn is the scheduler, and then there's pretty much compute nodes that work is being distributed across. So can you kind of help us navigate the difference between, let's say, Hadoop and working with an HPC stack?
Yeah, I think, like you pointed out, there are some similarities, but there's more differences than similarities. First of all, both were built for a completely different purpose. So Hadoop was built for streaming data processing, basically sequentially sift through large amounts of data to identify certain patterns for analytics purposes. Also, conceptually, it's different in that it brings the compute to the HDFS nodes that store the chunks of data that are being processed. In HPC environments, it's the other way around. So your scheduler schedules a workload, and then through a shared file system, the data is brought to the compute nodes through the shared file system. I/O is typically not sequential. and I/O is typically not sequential. And the other thing is most applications require POSIX compliance in the high-performance computing space. HDFS is not a POSIX-compliant file system because it was built for streaming large amounts of data, right? But again, like you pointed out, there's also some similarities. Hadoop includes the Yarn resource manager and scheduler to orchestrate job and task scheduling. And that's conceptually similar to what HPC schedulers do. So there is some overlap, but built for a different purpose in a nutshell.
Good to know. Good to know.
Any other questions at this point?
We have a couple of compliments for some of the points that you're bringing up, but I'll share that with you after the fact. Okay. I think everyone's excited to see the demo. Okay, cool. Yeah, let's have a quick look at the demo. This is actually something that you also can find online that I'm just going to walk you through quickly. If you just Google GCP with HT Condor, you're going to end up at this demo. The deployment manager config files are available on GitHub. But anyway, so what are we going to do here in this demo? We're going to build a little HPC cluster using Google Compute Engine instances, and we're going to use Deployment Manager to instantiate that entire cluster infrastructure. And then once that infrastructure is up and running, we'll have a cluster where HT Condor is installed on every single node. That happens at instant startup of that node. After the installation, once the cluster is up and running, all the compute nodes. So there are 3 different types of nodes here in HT Condor. There's the concept of submission nodes, a central manager, and compute nodes. When the cluster comes up, the compute nodes register with the central manager, and a user would log into the submission host, submit a job, the job would be queued up, and then the submit host would talk to the central manager as to what resources are available, basically which system to run the job on. And once the central manager replies with a host list, the submit host runs these jobs on the compute nodes. And in this case, because we don't have a shared file system underneath, we're actually transferring the executable that we're running from the submit host to the compute nodes. So let's have a quick look at the command line here. Can you guys see my command line?
Yes, we can.
Okay, cool. So what I want to show you here is the config files that we have for Deployment Manager. So that basically defines the infrastructure that we want to run. And this is one of the really cool things of Google Cloud, that we give you the tools to almost, write infrastructure as a code and express how your infrastructure should look like in a YAML file and in a Jinja template. And then with a single command, we can actually instantiate all of that. So the template we're going to use is called condorcluster.yaml. And the real magic actually happens in the Jinja template that we're importing here called condor.jinja that we're going to look at in a moment. But what I want to point out here is this sets the variables that the template then uses when it comes to instantiating the infrastructure. So one variable that we're using in the template is count, which is the count of compute engine instances that we want to allocate, the zone where these instances reside, and the instance type. And now if we have a look at the instance file here, this would be condor.jinja. Here, this really defines the complete infrastructure from scratch. So we start with the network that we define. We call it Condor Network, assign an IP range here. And then for that network, we set firewall rules. So the first rule allows SSH access here from anywhere. Then the second rule allows any node from within the cluster to contact to any other node. So you see here, this is the IP address range, the CIDR range of the cluster, and we open this up on all ports in the cluster. This basically helps us not worrying about opening up any specific ports that Condor uses. We just make everything wide open within our cluster itself. And then, as I said, we have 3 different categories of nodes. We have a master node, which is the central manager, essentially. We instantiate that in the given zone. Again, whatever has the keyboard properties here is what we pull in from the main YAML file. I think the zone was US Central, if I'm remember that correctly. And then we attach a disk, a boot disk to this master. And then one thing I want to point your attention or direct your attention at is the metadata. So we define the node and how it's configured, and then as metadata, we attach the startup script. So there's a fixed key called startup script, and when the node is instantiated and boots up, it actually looks at the value of the startup script key and executes that startup script. And what we do in the startup script is simply install Condor and configure Condor for the master. So there's not much to it. We see here we run apt-get install nettools vim, and then here's the key line. This is where we install Condor as part of the startup process. So what we're essentially doing is really boot up vanilla GCE instances, standard configuration, and then all the logic of cluster configuration happens in the startup script here. We're using here documents to configure the master. Then, of course, one implication of that is that every type of node, meaning startup, submit, or compute host, has a slightly different startup script it needs to execute to have the correct configuration. Okay, so second one here defines the Condor submit. It's essentially the same thing. It attaches it to the same network here, so this statement, and the only difference here is that we have a different startup script. And then lastly, we have the compute node that we define. And again, this has its own startup script. The only difference with between the compute nodes and the other nodes is that the compute node is actually part of an instance group. So after defining the compute node, we define an instance group. And the base instance name here is Condor compute instance. And it uses the property count here as the number for the number of instances that are part of this instance group. Remember, in the main YAML file, we had a count of 4. So we're building an instance group that comprises 4 compute instance nodes. And every instance group also typically has an autoscaler attached to it. But this is not relevant in this context because scheduling and resource allocation is handled by Condor itself. There is no autoscaling. So you see here for the autoscaler, we define the minimum and maximum number of replicas the same, which would be 4 in our case. Okay, so let's see if we can get this to work. So nice thing about Deployment Manager is that it is so easy. So we type gcloud deployment manager deployments list. We see there is nothing here. Then we say deployments create. We say this is my HPC cluster. And then all we need to do is give it that YAML file, Condor cluster YAML. And
so just to understand what you did walk us through here is, so Jinja is basically allowing us to templatize the creation of, let's say, this YAML file or this manifest that's being deployed or being used to deploy all the GCP resources, right? So that's kind of how we'd use the Jinja and the YAML together.
Yeah, thank you. Yeah, thank you for clarifying that. Exactly. So the YAML file in the properties section defines or sets these parameters that we then use, or that we can then use as for the corresponding placeholders in the Jinja template. Right.
Perfect.
So like node count, for example, or zone, those were, if you remember, we saw them as properties in the Jinja template.
Fantastic.
Okay, cool. It looks like already completed successfully, but it may still have to do some setup work. So I'll just like to resume the presentation and then revisit later on, because the provisioning is complete, but we still, on every node, we still have the startup scripts pulling down Condor, installing it, configuring it, so that may take a couple of minutes.
Mm-hmm.
So in the meantime, just want to talk about a couple of alternative cluster architectures to look at. I mean, this is great if you want to quickly build a cluster and then do your work, tear it down again. But there's also other concepts, one of them being dynamic clusters. So if you look at some advanced schedulers like Spectrum LSF, Resource Connector, or Univa Unicloud, they support this concept of dynamic clusters where you can grow your cluster on demand. So unlike a typical cluster that distributes workload over a given set of resources, these schedulers actually have the ability to interoperate or connect with an orchestrator that handles provisioning of virtual machines. So a simple scenario where this would be incredibly useful is a user submits a job that requires a massive amount of resources, high degree of parallelism, and there's not enough resources available. Well, with this configuration in a dynamic cluster, you can have the scheduler talk to an orchestrator and say, hey, I need X number of nodes to accommodate this high priority job. You can configure this at the queue level. For this high priority job, please give me additional X nodes. The orchestrator goes out and instantiates additional nodes in the cloud, goes back to the scheduler, says, I got additional nodes for you, go fire, and then the scheduler can dispatch the job. When the job is complete, these resources can be torn down again. So I think this is a very cool way to grow and shrink the cluster and leverage the elasticity that the cloud provides for these high performance computing workloads. Another idea is the concept of a meta scheduler, where you build a cluster of clusters. You have 2 layers of scheduling. You have 1 execution cluster for 1 type of instances, and then you have a meta scheduler that forwards jobs to the right cluster that's the right fit for a given workload. And then if there is low demand for a specific instance type, the meta scheduler can actually also deallocate these clusters. Or if there's a very specific resource requirement that has to be accommodated that there is no cluster available yet for, the meta scheduler can actually provision additional clusters using things like Deployment Manager. So you have scheduling at 2 levels, and you have what I'd call a cluster of cluster. One of the drawbacks is we have an internal prototype, but this stuff is not really available out of the box. There's the Globus toolkit, there's grid schedulers, but it always requires some type of cobbling things together if you want to run this model. Couple of comments on shared file systems. So typically HPC clusters rely on a shared file system. I mean, it's kind of intuitive, right? You have a cluster, you don't know on which nodes your workload is going to end up on. It makes things a lot easier if you can rely on the fact that every node has the same visibility into a file system for I/O. The other thing is that HPC applications, some of them have been around for a long, long time. They typically require POSIX compliance, which basically makes it close to impossible to use things like object stores for I/O and for a lot of HPC applications. So just to give a lowdown, and this is probably quite subjective and tainted by my personal experience of the file systems that are out there for this purpose that fit the bill of POSIX compliance, at least to a degree. And are shared is NFS, of course, comes with every Linux distro. It's very easy to set up. The problem with NFS is, of course, limited scalability. So you have one NFS server. If you think about a super large scale parallel application, doing I/O against a single NFS file server, that NFS file server is going to get very busy and potentially overloaded. Then there's Lustre. That's a high performance parallel file system. It's open source. Intel has put a lot of muscle behind Lustre. They bought a company called RamCloud a while back. They provide commercial support. There is canned Lustre solutions from companies like Data Direct Networks. My opinion is Lustre delivers very, very high performance. You got to be careful though which version you pick, as there may be some reliability and stability issues. Then there is GPFS. It's a proprietary high-performance parallel file system from IBM. It has enterprise features built in, such as hierarchical storage management, where you can even use cloud storage as a storage tier for the file system itself. So you have one view of the file system, but where the data is actually stored could be on block level storage, or it could be in the cloud. It has been around for a long time, is very stable and solid. The biggest drawback compared to all other three solutions is that it costs money because it's proprietary. And then there is GlusterFS, which is an open source parallel file system, which works great, but it doesn't scale to the extreme.
Right. And I think we have a couple of solution papers covering how to like set up Gluster, for instance, on GCP. So we can throw this into the chat. I do have a customer. I'm not sure if you've heard of this one, Arend, but Elastifile. Elastifile is something that I have a customer successfully utilizing with kind of an HPC configuration, and I think they just announced GCP support a few months back. There are definitely a handful of options out there as far as configuring the storage or data tier for an HPC cluster.
Yeah, absolutely. This is, as I said, tainted by my own subjective view here. There's a lot more out there. There's also a Avir that helps with NFS caching for hybrid clouds, things like that. One more thing that may be an option in some corner cases is that for read-only, you can actually mount a virtual disk and have a virtual disk mounted from multiple nodes. So that's like a poor man's shared file system, right? You just attach at the block level, you attach a disk read-only to multiple nodes. That gives you a shared file system for read-only, which might come in handy for some workloads. The other thing to keep in mind, and I say for now, we don't really have a managed shared file system offering at this point. So if you want a shared file system, you have to kind of roll your own using direct attached storage on GCE instances, and then whatever software you want to put on top of it. I think that's going to change in the near future, but this is the status right now. Okay, cool. So now I want to talk about a couple of customer examples. One customer is a digital effects studio called Atomic Fiction. They've worked on big movie productions like Transformers, Star Trek, Flight. And one thing that's really very specific to this industry, even more, I mean, it pertains to all industries, as I mentioned earlier, the burstiness. In media and entertainment, there's really an extreme level of burstiness of workloads here, really. These studios, depending on where they are in the production cycle of a movie, can really have their resources idling or be completely maxed out. And this is actually reflected on the graph here on the right side here, where you see that on March, I don't know which year it is, but in March, the company was running 2 million processor hours, and December they're running pretty much nothing. So this basically cries for cloud elasticity and using resources on demand. So this is what happened to Atomic Fiction. They needed this overflow capacity, and they needed it provisioned quickly. They built their own scheduler to orchestrate GCE instances for their rendering jobs, and they used up to 15,000 cores at the same time. But what I find really interesting about this is really the slide from the CEO, because we can talk a lot about the benefits of hybrid and cost and this and that, but what he's actually saying here is that it really unleashed their artists' creativity. The artists could really implement ideas that they would not have been able to implement and try out without this, which I think is very powerful.
Yeah, that's really great.
Another example is Schlumberger. I don't have a lot of detail there. There was a blog that came out by our senior VP of infrastructure, Urs Hursley, last week. And that's all the data I have on this, but I still wanted to bring it out there because Schlumberger is one of the leading providers of software and technology, and as well as data in the oil and gas industry. They've been around for 90 years, and every major oil and gas company uses their services in one way or another. They have a data processing platform called Omega that they ran or ported to GCP using custom instances and NVIDIA GPUs, and they used their cluster delivered 35 petaflops and 10 petabytes of storage. So they really ran some massive workloads on GCP. And as far as I understand, they're they're really convinced of GCP being the right way to go. They were on stage at Next
Oh yeah,
16, and yeah, we have a very close relationship with them.
Absolutely.
Sorry?
Yeah, I'll share that video with the group here.
Yeah,
it's a pretty cool keynote. So
cool. So now let's switch gears. This is what I had on the presentation part. I think we got a few more minutes. I just want to quickly show you what's going on with the cluster we set up. So if we say G-Cloud compute instances list, we see a list of instances here. So we see we have the 4 compute nodes that were provisioned, the master and the submission node. And then we can say G-Cloud SSH compute G-Cloud compute SSH, and we can log into the submission host. Okay, and now using the Condor commands here, we can say Condor status, and we see that the cluster is up and running. So we see our 4 nodes here. Now this is the feedback, not from GCE. This is what the schedule actually says, right? So the schedule says I have 4 nodes under my control. And if we want to run a little example here, we just go to applications. A simple prime number crunching application. C minus O. Just have to build it quickly. And we can see, so the way jobs are submitted in Condor is it's not command line and argument, it's actually a submission file. So this is already prepared here, called submit primes.
very nice.
It's a little bit cumbersome that you have to edit a file every time. Like I come from the LSF scheduler world where you can just type the submission on the command line. Here you have to actually edit this file, but that's okay. Not a process. So what we see here is we see the universe. There's vanilla and standard. It basically boils down to whether you need checkpointing or not. If you need checkpointing, you would run it in the standard universe. And then primes is the executable we're running. This is how far we go in searching prime numbers, where the log files go, the job statistic jobs, where the output goes, if files should be transferred, and then how many jobs we want to run. Let's bring this down to 10. Save this. And then we can just say Condor submit and submit this. So we see here 10 jobs were submitted to the cluster. Okay. And if we say Condor status, we actually see now that, so before we had zeros here, now we have resources claimed, which means we're firing on all cylinders here, right? Condor is claiming for this job the 4 cores that we have. So these are single core systems, and we're using all 4 cores right now to run this calculation. And if we look at Condor history, we actually see we're already done here. From 10 to 19, these are all the individual prime number jobs that we ran. Okay.
Very nice.
And here, because we had the output file specified, we actually see with the index the result, the standard out of every job that we run. So prime.1 says this machine calculated. So we see we actually really ran this application.
Very cool. And you can kind of and I guess this is a little more HPC specific, non-specific to GCP, but you can specify different syncs that are, or does it kind of stay within the cluster when you do process these jobs, right? Can I identify multiple syncs that I want end results to be written to, or how does that kind of work?
When you say sync, you mean output locations for a standard out?
Yeah, does it typically stay within that file system of the cluster, or can you, like, let's say if I wanted to have HPC write to somewhere else where I'm taking these end results and maybe performing some type of analysis, does HPC fit that use case, or is that where you'd have to come up with some other type of glue?
Yeah, absolutely. I mean, you basically, and this is all application specific, right? You submit the
Sure.
the application writes to whatever is configured in its configuration files, right? So you just have to make sure that that data location really does exist, right? Whether it's a shared file system. And in this case, actually made our lives easier, right? I said, we don't have a shared file system here, but the executable was automatically transferred because Condor can do that for you if you don't have a shared file system. It was automatically transferred to the execution nodes. See here, because we have the still transfer files if needed. So this for applications that don't do a lot of I/O or where you just don't need a shared file system, this is a nice way to do it. Just have Condor take care of it. And you can also do this with input files. So you can copy input files before execution to an execution node and then copy them back afterwards as part of Condor. Like it provides options at job submission time that allows you to do that.
Got it. No, that's super helpful. And I think this has been a great overview. I think you have a couple points you want to wrap up with, but I just want to thank you again for your time. And next time the demo will be, I'm hoping it'll be rendering some Star Trek footage, right?
Yeah, we might need a little bit more time then, though, because animations these days, right? They're so involved that these rendering jobs take a long time.
Oh, for sure, for sure. Great.
Okay, cool. Yeah, let me just quickly wrap up with what we went over. So overall, I think it's fair to say that GCP is a really good platform, HPC workloads, providing the latest technology, the pay-as-you-go, the preemptible instances, again, very useful in conjunction with checkpoint restart, and the idea that you can extend your private address space into the cloud for hybrid clouds seamlessly with this dedicated interconnect options. GCP also has the right tools for cluster deployments. We looked at deployment manager, managed instance groups, startup scripts. This HD Condor thing is a really good starting point for whatever you do. Even if you want to deploy a different scheduler, you can just edit the files and it will save you a lot of time using that as a starting point. And of course, there's a variety of schedulers available. I think we only scratched the surface there that can meet your requirements, different scheduling paradigms. We looked at dynamic scheduling. There's also things like multi-cluster where you can get master schedulers to talk to each other, transferring workloads. So there's a lot out there, and I'm sure there's something that can meet your requirements here. So we looked at the dynamic schedulers and at the meta schedulers. Okay, cool. So that was it from my end. How about questions?
Yeah. So I think a lot of the questions, they kind of were addressed mid-presentation, and I've also kind of just been, kind of working on the chat here. So I think we're all set. I think, again, excellent presentation. This has been, if anything, incredibly helpful to me to understand HPC as well as how it plays not only on GCP, but how it helps multiple use cases in different industries. So awesome job, Arend. We appreciate it.
Yep, you really showed how streamlined the deployment process is. So thank you so much. That's very helpful.
Okay, thanks to both of you. Okay, goodbye.
And thanks to everyone else out there for joining. Take care.
Thank you, everyone.
Thank you.